Welcome to today's webcast, Using Microsoft Azure Machine Learning to Advance Scientific Discovery. I'd like to turn today's event over to your presenter, Roger Barja, Group Program Manager for Cloud Machine Learning Group, Microsoft Corporation. Roger, you now have the floor.
Great, thank you, Kim, and thank you everyone for joining the presentation this morning. Last week we had two exciting announcements. The first was that we announced the public preview for Azure Machine Learning, which is a fully hosted cloud service for machine learning and data science on the Windows Azure cloud. This is something our team has been working on now for the past 2 years, working with researchers across Microsoft Research to pull together some of the best machine learning algorithms, but also looking at what are the friction points that people encounter in using machine learning, and more importantly, how can they deploy their solutions into production as fast as possible. And I'll be telling you more about the service today. Another exciting announcement we had last week is that we announced the Azure ML for Research program that's being managed by Microsoft Research. And this is very cool, because what this provides is there's two types of awards that one can apply for and get from Microsoft Research. One is a data science instructional award, where an individual student will actually get an account on Azure ML, and along with 500 gigabytes of cloud data storage for each student, which a university can use to actually teach an entire data science program or applied machine learning program. And again, this program is available to academic and nonprofit institutions, and there's a selection process that goes on to actually choose who gets admitted into the program. And a second offering within this program is actually for large research collaborations, in which we'll offer a shared workspace where a research group can actually store a large volume of data, up to 10 terabytes, to enable a group of researchers to work together to try to actually analyze the data, gain insights together. And because Azure ML is collaborative, the data scientists, the researchers working against this data can be anywhere around the world. And they can share the models and put a predictive model into production as a machine learning web service for a community to offer. Now, the first deadline for proposals for this program is September 15th. The next deadline will be November 15th, and every 2 months after, they'll be reviewing proposals. You can actually apply online at the link that's provided at the bottom of this page. So again, two exciting announcements next week. Now, we have a diverse audience listening in today, and so instead of just diving in and talking to you about and showing Azure ML, which I will later, I actually wanted to just step back a little bit and say, what's going on in machine learning? Why are we so excited about machine learning? Why is the industry getting so excited about machine learning? What is machine learning, and how should we be thinking about it and its potential impact? So I wanted to spend just the first 10 or 15 minutes just sharing a perspective, just an overview, if you will, on what we've seen the power of machine learning. Then I'll turn the conversation over into, why did we build Azure ML? Why did we choose the features that we've chosen for this first version of Azure ML? What's motivated us? What were we hearing from users, potential users, that actually influenced what we built? Then I'll spend about 15 minutes in a demonstration of Azure ML so you can understand what the heck this is. And then we'll close and open up for broad questions. Now, if at any point during the presentation you feel that there's a clarifying question that needs to be addressed, I would encourage you to go ahead and actually send it in to the moderator. Kim will actually then surface it to me if it will help, in the talk itself. Otherwise, we'll leave plenty of time at the end for question and answer. So, machine learning. Simply put, they're computing systems that improve with experience. And experience comes in the form of data or training sets. Now, in a world of big data, one of the first things that's really changed is that our customers, our researchers, are able to capture enormous volumes of data about a process, about an individual, that they actually want to analyze. So having ubiquitous data and relatively cheap compute has actually really made this possible for machine learning to actually be applied. The potential for machine learning, we actually view it as being one of the most impactful technologies that's going to shape IT, shape applications and services of any other technology out there over the next decade. We actually believe that it's largely unappreciated, and its impact is actually going to be profound over the next decade. And this hasn't gone unnoticed. I mean, for many years, Bill has been saying this. A quote he was noted for: if you invent a breakthrough in artificial intelligence so machine can learn, that would be easily worth 10 Microsofts. And even more recently, Satya Nadella, who's our current CEO, made the observation that over the next decade, computing will become even more ubiquitous and intelligent will become ambient. And that's actually very powerful. We have so much data floating around us. We have devices around us, all of this information. Imagine being able to analyze that and make sense of it. And at any point in time, our devices, our applications are going to basically be powered by machine learning to actually help us make smarter decisions. And in a world of connected devices, connected cars, wearables, we have this opportunity to basically be surrounded not only by data, but then augmented intelligence services. So it has great breadth and depth of its applications, and we're just starting to see the beginnings of it. And it helps to go back to the beginning. What was one of the first successful applications of machine learning, and how did it change the game? And one of the first successful applications was handwriting recognition. Now, in post offices, they were early days in the late 80s, early 90s, basically to actually figure out where a letter should be routed. There were systems, optical character recognition systems that were written. They were largely rule-based, imperative declarative code that basically would actually analyze, look for the letters, and actually run through a series of rules. Now, these systems were incredibly challenged by different letter formats, different handwriting styles, and they fell over regularly and required a large amount of maintenance, to the point where it just became untenable. Actually, the U.S. Post Office actually commissioned a large research grant funding call for proposals to actually try to find new ways to actually process it. And the actual way that was successfully implemented was to treat this as a machine learning problem. And we talked earlier that machine learning requires data. It requires training sets to gain experience. So how it was handled in this case is that individual letters from different handwriting styles were captured and labeled with the correct output. And in fact, lots of training samples. In some cases, they used computer simulation to add noise, rotation, and look at many examples, and then labeled that data. Fed all that into a machine learning system, and what you end up with is a relatively accurate digit classifier. But something very unique about machine learning, they never ship. They're never done. If they make a mistake, that's no problem. You go in and actually correctly label, put that back in your training set, and you retrain. And so this has actually resulted in what the state-of-the-art systems are today for optical character recognition, understanding documents and document understanding, is treating it as a machine learning problem and letting the data and a machine learning algorithm actually build the application. No handwritten code. It's actually learning from the data with machine learning. And of course, there's statistics underneath of the covers. We're not going to get into that in the talk. But basically, it changed how what was a previously challenging problem got attacked. And in fact, a modern implementation that you can actually go to the Azure Data Marketplace and download the Bing language translator. And when you happen to be traveling around parts of the world, you can actually point your phone at a menu in any language, take a photograph, tell it what language you want it translated to, and it will translate it into that language. Why? Because behind the scenes we've used machine learning from our Microsoft Research Technology stack to actually build a language translation system, recognition and translation system. So why do we do learning? Well, you learn it when you can't code it. Recognizing speech, recognizing images, written handwriting, gestures. You learn it when you can't scale it. Recommendation systems at the scale of Netflix or Amazon. This is not something you could write a recommendation system for by hand, but you have sufficient data on people's behaviors and what they do that you can in fact apply machine learning and build a highly accurate recommendation system. Similar with fraud, similar with spam. All hard problems that have all been successfully attacked through machine learning. And you learn it when you have to adapt or personalize it. Predictive typing on a small handheld device is now being attacked by machine learning. Actually learning my voice and actually building a highly accurate speech-to-text translator just for me in the way that I talk. So this is something you could not have a developer write a custom app for every one of your individuals, but you can in fact learn from individuals' data. And you learn it when you can't track it. AI gaming, robotic control. I mean, there's a myriad of applications where you have the data. It's an intractable problem to actually address by hand. Use the data and machine learning to actually build a solution. And hey, If it doesn't work the first time, if it's not highly accurate, that's fine because you're essentially building a training set for the next generation of the application. Now let's look a little bit at what's been going on over the past years and talk about what we can do today. You know, in the 1980s, when I was highly active in it, it was the connectionist or the neural network period of machine learning. And we were really looking at how to actually evolve neural networks. We did backpropagation. That proved to be a very tricky algorithm and a very tricky technology to get right with a lot of hand tuning. And then in the 90s, we started moving into the symbolic era of machine learning. Decision trees were actually the dominant method, that what was called CART, classification and regression trees. C.4.5 was the classic algorithm. And there were expert systems and rules as well that started to surface at that point. In the 2000s, we actually saw support vector machines and the rise of so-called kernel machines to actually allow us to tackle even more difficult problems in higher dimensions. We saw the real rise of statistical learning theory and actual scoring systems. This is where we saw machine learning was being put into production by Fair Isaacs and FICO scoring and risk scoring, where predictive models were put into operations and businesses started to run at scale over these models that were making predictions. And in 2005, we saw the rise of graphical models, where we're not just learning for the data, we're actually trying to statistically model the data. It was an interesting fork, and it's that exists today. Infer.net from Microsoft Research Cambridge is a fine example of that, where it's actually understanding the statistics of the data, modeling that and its dependencies, and yes, fine-tuning as you understand the distributions of data, but not just allowing a machine learning algorithm to learn from the data, you actually model it effectively. And more recently, and what's really been exciting lately, is big data and deep neural networks. I'm not going to cover it in the talk today. We will have support for deep neural networks. In fact, we do in our current release for Azure ML. But its implications for truly understanding what's in an image, truly understanding language translation, and actually being able to learn multiple languages at the same time is profound, all because of basically the work that started back in the 80s, which has continued in neural network theory to the point we can train arbitrarily deep neural networks. But the real turning point here has been the fact that we have large-scale compute in the cloud in particular, or GPUs for deep neural networks, for example. We have tons of data, and we can now actually apply this data. Even the simplest of algorithms, when given large quantities of good data, can actually become highly effective machine learners. Let's just look at a couple of examples here within Microsoft before we turn our attention to Azure ML. The Xbox Kinect was clearly a commercial success for Microsoft, but it was also an incredible technological success. If you look at and have played with the Kinect, you realize that it watches your gestures, it figures out what you're doing, and if you think about the diversity of challenges that had to be faced there, you have individuals in different postures that you have to be able to recognize. You have individuals of different body shapes and sizes, different ages of individuals. So the relationship, the whole ratio is completely scaled. Individuals will have accessories attached to them, and you have to be able to figure out still, is that their arm or is that a purse? You have to be able to pull foreground out of the background. You don't have to clear your living room. You can have plants in your living room, couches in your living room, lights. Yet that Kinect sensor can still actually figure out where the individual is in the room and what to ignore. And in fact, when you can do multiplayer, you have multiple people in the room, and guess what? It actually tracks each individual independently and is able to understand what they're doing. This is clearly one of those problems that could not have been tackled without big data. And in fact, how we built it, again, it's a machine learning system, so we're going to have to build a training set. We had individuals wear these sensor suits in which we could actually record their gestures, label what they were doing, building a label training set to feed into a machine learning system. And this was no small task. Actually, we had 800 million training examples from individuals. And that was kind of expensive to do, to spend that time with that individual in that suit and capture that data. So we actually, and we needed to get the performance, actually simulated using both machine learning and simulations to add variations, add noise, do rotations of these individuals to create another 800 million training samples. By the time it was done, we had roughly 2 billion training samples that we had to fit in. This is the era of big data and big compute meeting machine learning. And that was fed into a machine learning system. So the Kinect sensor that you see today and are interacting with when you pay Xbox is basically being driven by machine learning systems. The same machine learning algorithms are actually in Azure ML to allow you to tackle equally hard problems. And there's a couple other cases that you may not be aware of that we've actually applied large-scale machine learning. And search. We've actually treated search as a complete machine learning problem. And in fact, all the results that you see, no less than a dozen machine learning algorithms have shaped, influenced what you see on the screen. Everything from what links are most likely to get clicked, and we'll actually put down those closer to the top. Was something misspelled? Did you really mean to type something else in which case we'll actually go ahead and correct the spelling and do a search on what we think is the correct spelling, but also put a message up there saying, did we get this right? And you can see, or if you should be connecting the dots, we're actually going to build a training set from all this if we got it right. What language were you speaking in? What was your intent? And we've been watching, we watch the series of searches, we look at the actual words that were used in the query to say, are they trying to find information? Are you trying to make a purchase? Are you just serendipitously surfing? And based on that, bring up related searches, which we feel are contextual based on your search, the words that you've used. Behind the scenes, before we serve up a page, we've actually run an ML algorithm to see if the page is malicious and filtered it out so you only see what we believe to be safe pages. And we're also serving up ads, and we're asking the question, what's the probability of each click on each ad? And that often deals with what your context is, what you're doing, or what's your intent. Are you trying to buy? Or are you just, again, looking for more information? What ads to show and in what order? And afterwards, at the end of the day, what pages should we re-index to actually improve the performance? And your clicks and your choices that you make in the search and how far down you have to go to make that first click all become information for us to actually retrain and recalibrate our models every night. And really, machine learning enables just about every value proposition out of web search. And in fact, the more people search and the more people use, the better the system gets. It learns over time. Here's another problem which actually some might find interesting and applicable in their domain, is a really challenging problem. You know, we in our data centers, this is what you're looking at are logs coming off of our Office 365 hosted exchange from our Dublin data center. Now, our data center operators are actually, very smart individuals. They're looking at dashboards that are monitoring their servers, the services, the networking, the temperature, and the services themselves are giving us feedback. And they attacked it in a traditional manner. They wrote a series of rules, handwritten rules and code that would monitor, look for KPIs and spikes. But, darn it, it never really helped them with finding the root cause. And so after several months of not being able to predict failures and not being able to rapidly diagnose a failure, we decided to treat it as a machine learning problem and actually captured all of the sensor logs that were coming off the machines, the network cards, the services themselves, other ambient information within the data center, and started capturing them as logged, time series logged. And when an event happened, we just simply had the operator press a button saying, this is the type of event. A service failed, a disk drive failed, a whole rack went down, or I had to reboot the service itself. And let machine learning actually analyze the data and figure out what the root cause was. So hundreds of thousands of machines, hundreds of metrics and signals per machine, and really allowed machine learning to actually find out what correlated with the real problem. Because again, just because it happened once doesn't mean it was actually strongly correlated. We had logs from months. And also, how can we basically extract effective repair? Could we do predictive models that says this disk drive is going to fail and the next week you might as well replace it now, or this server is going down. You might want to move load off of it to other servers. And so now our monitoring is to a large part shouldered by large-scale machine learning. So hopefully those of you who are thinking about how you might actually apply this technology have got a little bit of a better sense to the kind of applications to which you can apply it to. Sensor data, actually user interactions, services, even actually predicting what individuals are doing off of images. So if we think about machine learning, it really allows us to solve extremely hard problems better. It allows us to extract value from big data and drives a shift in data analytics. And there's actually kind of something a little bit more subtle going on here. It's really about changing your way of thinking about a problem. It's about getting the data, getting labeled data, getting good data, and actually trying to let an algorithm build the solution for you. And again, it doesn't have to be perfect, but as long as you have a feedback loop, you have a chance to actually iteratively improve the performance of an ML solution over time, which is really compelling. So a large number of scenarios. We've got and had exploratory projects in almost all of these, all the way from predicting who is going to basically return to a hospital after being the readmission rate, doing telemetry data and analytics for connected cars, predictive maintenance and manufacturing, churn analysis, life sciences research, targeted advertising, smart meter monitoring. I mean, we've had a number over the past year with customers and researchers we've given access to of these applications of applying machine learning. There's simply no limit to the kind of applications to which this can be applied. All you need to have is data, the ability to label that data or give feedback, and access to machine learning at scale to actually start making sense out of it. So this is where Microsoft Azure Machine Learning comes in. Now, we've made some intentional choices about the functionality we're releasing in this first version, so I kind of want to walk you through that and why we made the choices that we made. Then I'll actually give you a demonstration. We'll spend a little bit of time wallowing around with the service so that you have a really clear idea of how you could use it and what it can do for you. The first was, we could have focused machine learning on a lot of things: image analytics, speech analytics. We instead said, look, where we see people getting the most value is the ability to develop and deploy predictive models. And not just build them and keep them on your workbench, but actually put them into production as a machine learning web service with a REST API. And we'll do it together today in a quick demo. We'll actually grab some data set, we'll train it, we'll evaluate it, and we'll actually publish it as a web service within minutes. Nobody else can do that out there today. And the reason we did that, again, is just the breadth of applications. And another issue we wanted to address is that the two impediments to why people aren't embracing predictive analytics as much as they are today. The first, there's actually a handful of reasons, but one of the main ones is the time it takes to put it into production. So I talked about, that we could put a model in production in a few minutes. Out in the real world, it can take 3 months to a year to put a model into production because it's called a code porting exercise. You build it in our studio and then, or any other favorite tool, and put it in production. You have to roll up your sleeves and start sitting down with the developer to write code. Our target user is a data scientist, and specifically what we're calling, emerging data scientists. This tool does not require a PhD to use. We really wanted to make a tool. We're seeing a new generation of data scientists coming out of certificate programs, self-study. They're moving over from their BI profession or their technical computing profession and getting interested in exploring data. And we wanted to make a tool for these individuals to be highly productive and build models that are just as good as somebody who may have been doing this for the past decade and using SAS. And again, we're optimizing for the fastest time to a deployed solution. And something else which was inspired a lot by our work with researchers in the sciences early and understanding that businesses was moving that way is its support for collaboration. We'll talk about it in the demonstration and we'll talk about it a little bit more, but we support collaboration and sharing. It is meant to be an experiment platform. You can share data with researchers anywhere around the world. You can share your experiments with members of your group or other research groups. You can even share the finished web services that you build and maybe make calls to them to augment your web service. So again, support for collaboration and sharing was key to this, something we heard from researchers, but also from business users. One of the things that we heard when talking to people, access to high-quality ML algorithms is hard. It's either expensive, but the reality is one package might have very good decision trees. Another ML package has great neural network support. Another one's got some pretty darn good support vector machines, and you need them all for various applications. But having to learn 4 or 5 packages, it was a mess. And the affinity group was about on the order of a dozen packages you had to have access to. And it's not just ML. If we're trying to actually, we're doing data science. We're reading raw data in, we're cleaning the data, we're selecting features which have the most information, we're trying out different ML algorithms and running experiments, we're going to evaluate which one is best. So you really need to have end-to-end support. You shouldn't have to use multiple tools. And then finally, that ability to put a model into production, which I've mentioned already. Some of our guiding principles was there should be no software to install. If you have a Chrome browser running on Linux, or if you happen to have IE or other browsers we'll be testing over time, you're good to go. There's no software to install. It's a fully managed cloud service accessible through a browser. So nothing that basically prevents you from getting on and doing data science. It is collaborative. We'll actually show you today how you could actually invite somebody to join this workspace, which is, I'll talk about what a workspace is in the demo. And we've tried to minimize coding to the extent possible. You'll see that we've got modules, which have actually, they're behind that box, which we call a module. There's actually hundreds, maybe thousands of lines of code implementing an algorithm. To you, the user, the data scientist, they don't have to think about that. They simply say, I need to read this data source, and they drag a module onto the palette that actually reads the data source. Oh, I've got to clean missing values. Well, you drag a module on that cleans missing values and connect your data set to the missing values replacement, set the parameters on how you want missing values replaced. When it comes time to create a training set, you drag a module on that does that. You tell it whether to stratify it or how to split it between training and testing set. So you're really thinking about your data and your experiment you're trying to run. You're not thinking about writing code. Something else which we're not going to get into today is that those modules, you don't know. One of them could be a Hadoop job. One of them could actually be reading and running its execution on SQL. One of them is actually running an R package on a pool of R servers that we have behind the scenes. So it's something else we've factored out. You don't need to learn all these different systems. Again, you're just thinking about what you want to get done. We are running an orchestration and coordination engine behind the scenes that moves the data, transforms it from an R data table for the R services to a R internal data format, or maybe back over to HDFS. And it's extensible. So we have support today that you can write arbitrary R code. We will have support for Python. There's over 400, roughly today, 400 R packages that we've uploaded, and we're going to allow you the ability to upload R packages, not in the current release, but in an update coming soon, so that basically if you happen to find an R package that looks very compelling to you, with a few clicks you could actually add it to your workspace, your private workspace that you and your team have access to. We also have an SDK coming out later this year, which in fact you might say, hey, I'm going to actually wrap some of my own code I've written. I've written a simulation engine, or I've written a rules engine or an optimizer. You'll be able to create your own modules with the SDK. And then finally, what you'll hopefully notice in the demonstration, it's an experiment platform. Data science and machine learning is really about running experiments. There's no rules on what ML algorithm is best. So we want you to experiment and experiment fast and be able to do side-by-side comparisons, roll back to what you were working on 2 days ago and fork off and start from there. So basically you can try things out. But once a model has been built and put into production, it becomes immutable. So if your research team has built a model for making a prediction about weather, about earthquake, whatever, and the team has decided that's the model that they want to run on, it becomes immutable. But it's not invisible. People can actually search for it, they can discover it, and they have the ability to clone it and create a copy of it and start from there. So that allows you basically to protect your valuable models, but also allow other people to actually reuse them. And then again, we keep hitting this on because it's the key differentiator that nobody can do today. Quickly deploy it as an Azure service to our ML API service that will host it. Might make sense to just say a couple more words, just a few words about the API service, because this is pretty powerful before running the demo. Increasingly, we're moving into a services world. Sometimes we think about big monolithic services. In the future, apps are going to be made out of hundreds, maybe thousands of microservices. And so this ability to say, I've just made a predictive model that is going to predict whether this was spam. I've made a predictive model to figure out the intent of the user. And so when creating a web page, for example, or a web page result, making calls out to these dozen, ML services makes perfect sense, and to actually shape or influence the final result. So, and having an API service that you can call and say, what models do you have in your repository? What's their API? And then you can make a REST call to it. Allows for incredible agile composition of these web services. But when you put a web service or your model into production on our API service, actually, we don't spin up a VM and start charging or just have it sitting there idle. Instead, we intelligently keep it indexed and hot. If a request comes in, we pull it into a hot VM pool and start serving up requests for that model. When there's no more incoming requests, we quiesce the model. Or if somebody, maybe the whole research community is pounding away on a model, we can actually start scaling it up across multiple VMs to satisfy the SLA that's been set. And we have two modes that we support today. So when you put a model into production, you actually get two instances of your service. The first is a request response, which means you send a record in, you get a record back with the scored results. So is this transaction fraudulent? Is this patient going to readmit? Or batch mode, where you could send in an entire file saying, hey, here's 100 patients that checked out last week. Please give me a list of which ones are high risk that I should actually follow up on. What you get back is a file of scored results. And there's some monitoring and telemetry we provide to the person who's hosting these models so they can see which ones are getting used, by whom, and how much data is going through them. So there's capabilities there as well. So I'll be spending most of my time talking about ML Studio or showing you ML Studio, but there's that second back-end model management service, which is really powerful. So with that, I'm going to stop and go over and actually run a demo. And Kim, sometimes when I change from PowerPoint over to browser, sharing stops. So please let me know if sharing is still going on.
Okay, I'll let you know.
Thank you. So everybody, what I just did is I just opened a browser. I just logged into my workspace, and I could have opened it with Chrome as well. And I'm in what's called my workspace, which I had mentioned to you earlier. And usually on first-time users, what you land in is basically, hey, welcome to ML Studio Preview, which has a forum that you can ask questions. We respond. Other users in the community can respond as well. We have all of our online documentation for how to use the service, updates of what has changed, and samples, both experiments that we've built, a gallery of sample experiments with sample data sets to get you started, videos that'll actually step you through how to use it. But really, when I do my predictive modeling work, what I land into, this is my workspace. And what I see here are samples that Microsoft has shipped to help you get started. Everything from doing time series forecasting with ARIMA, which are all R packages, back to how to use different functions, such as how to read a data set, how to do cross-validation. Let me just expand this out. These are all out of the box to help you get started. Using regression, binary classification, multi-class classification, some UC Irvine reference data sets that we've built models for breast cancer detection, flight detated German credit. These are all either from UC Irvine or former KDD competitions, down to basically how to make best use or best practices in using our service, sentiment classification, for example, to allow you to do sentiment analysis. And you can see you can actually build arbitrarily complex DAGs. All these are documented, what we've done each step, so you can actually read how we've used the service to help you get started. And I can also see, I've obviously not been busy because I click recent work and it says, Roger, you haven't done anything recently. I can actually go and see the experiments that I am working on right now. These are models that I've built over the months. But I'm not limited to just my own workspace. I can actually say, hey, I want to go join one of my colleagues, Mona, and go work with her on an experiment. She's given me access to her workspace, and I can go work with her on a problem. Or I can go work over with my colleague Manish. So I can bounce around between different workspaces and literally change the projects I'm working on. So for example, for the academic program, an entire class can have a workspace, or they can have their own workspace and students can work together, or researchers can work together. Let me go back to my workspace. And I may decide that, these are our videos here, I may decide that I need some help on a project. And so I can simply go over and say, want to invite somebody to join me. This is where I would type in their live ID, which is their email address. I would basically set them as an owner, which means they could delete and do whatever they wanted to in the workspace, or just a user, which means I want them just to work on models with me. Hit send. They get an invite. They open up their browser, hit the link, and they can immediately join me here in this workspace, and we can work together. Let's actually take a little bit of a tour. First stop though, let me say new data set. Somebody could have given me a data set from my local file, and you can see here that we can upload to the cloud from ML Studio, from the desktop, CSVs, tab separated files, text files, a zip file, an R data object, an ARF file format. That's how one way of getting data in. Now this is the authoring experience. I said let's create a new experiment. We're going to create a new model together. And what you notice is a few things have changed here. This is the authoring palette, which is kind of a hint to, hey, drag stuff on here to get started. But you'll also notice over here on the left, I have drawers available to me of functions. These are models that I've trained and put into production. These are data sets that I've uploaded. Data input and output, a generic reader. I pop this guy on, open up the dialog box over here. I can read from blob storage, Azure table storage. I can read from a SQL database on the cloud, an HTTP site such as the UC Irvine, or maybe you set up an HTTP server to serve up data. Run a Hive query over Hadoop, run a Power Query, all from this module. And you see as I make these choices, the dialog box changes. This is the necessary information this module needs to run. That's the extent to which we have to do coding. Let me just take a data set. In fact, well, let's do one other thing. Let's just get started with something. There's actually a very simple demo I like to run, and it's this bike buyer. I've got 2 years of customer data of people who have been buying product from me. And in fact, if I just click, visualize, we generate HTML5 so we can visualize it on any browser. There are 10,000 rows in this data set, 13 columns. There's bike buyer, whether you've bought a bike from me or not. I click it. I can actually see the frequency. Go ahead and close that. That's interesting. Oops, didn't mean to close that completely. But from this pop-up, I can actually get all the metadata that I need. Marital status, it's pretty good mix of single and married. Gender's balanced. I can see income is not. Children, oh, that's interesting. It's like most people don't have children in my data set. Different education levels. If I scroll down also, do I have any missing values I have to deal with? So I get a lot of information from this visualization. At any point in the workflow, we have this information available. I just have to click the pin and it will actually show me what's inside my data set. So I don't have to deal with missing values. But if I did, everything's searchable over here. Not only is it in a drawer, but if I just type in missing, well, there's my missing values scrubber module. Go ahead and delete that. I don't need that. In the interest of time, let's just go ahead and create a training set. And let's just split it. And we're going to send the data set down to the splitting routine. Open up the dialog box. Just a couple quick things to note. I'm going to use 70% for training, but we also have support for stratification. Those in applied machine learning will know what this is. I mean, if I'm trying to predict in the future, I would use a timestamp column and stratify it. Only 70% of the data that was actually behind some timestamp would be used for training, the other 30% for prediction. So we can stratify just with the click of a few buttons. We don't need to stratify this. At this point, let's go ahead and just click run. Now this is the first time I've really done any execution on the cloud. I just sent the DAG up to our service, to a data center that's in our South Central US. It's done. I open this and say visualize. And sure enough, 7,000 rows. The distributions look good. Nothing's really changed. That's my training set. So at this point, let's just go ahead and train. We have a generic trainer that can train any ML algorithm. Needs the training set. I'm going to need to score, which is basically I got to test the performance of the model on data it's never seen, this holdout data, which is a great proxy for how it's going to work in the real world. And because I like to look at things and run experiments, I'm going to need to have something to evaluate different experiments. And we have that as well, this evaluate model. Let me just shrink this down a little bit. It's getting a little cumbersome. And close that. So at this point, it's like, okay, well what ML algorithm are we going to use? Let's go ahead and close this up. and just give you a sense of what we have available to us. Again, we can do filtering, cleaning, transformation. Everything that you need for doing data science end-to-end is here. Open machine learning. Close these drawers that I had opened. We're doing a classification. Are you going to buy my bike or not? And so you can see we have a large number and growing daily of classification algorithms. So I'll go ahead and I'll try, I'm going to try a two-class logistic regression. I don't want to do regression, I'm doing classification. We'll actually say we're going to go ahead and do two-class average perceptron. Simple neural network. That's the model we're going to train. Now at this point, we've got a red bang here that says, hey, I need some help. This guy needs to know what column we're trying to predict. Well, we're trying to predict whether you're a bike buyer or not. That's it, everybody. I mean, minus the narrative, it would have taken me all of a minute to author a machine learning experiment. I click run. This DAG is being sent up to Azure for execution, and it'll start giving me some progress bars. So its split was already done. We're loading the perceptron model in and configuring it. We're now training it until it converges on the best trained model it can with that training data. It's trained. Now we're scoring it on data it's never seen before. And we're done. We've actually done the evaluation as well. Now, of all the metadata here for this experiment, let's see how it did. And what I'm looking at here, we're pulling out a lot of data information. I have a feeling a lot of people are hitting the service this morning because it's running a little slow.
Roger, while that is loading, we do have a question.
Yes, please.
It says, what is the technology to capture the data? How would you capture the data for an IT environment? Let's say for an IT environment where we want to plan for capacity based on CPU, memory, disk, I/O, etc., or predict issues.
Okay, so we've done an application similar to that, and so what we did is that they put wow, this is running extremely long. We did interception at the devices itself, basically intercepting and writing to local file systems for the local machines. That data was then moved over to a Hadoop cluster where we ran Hive queries from Azure ML. I'm going to actually stop this. So basically the bottom line is you put intercept and logging data close to the service that you're trying to do predictions on, move those into files, then we can run Hive queries over them to actually aggregate and create the necessary information. So that is just not rendering. There we go. Yeah, so it didn't, one of them failed, one of them succeeded. Sorry about that, folks. That's a cranky model right now. Cranky visualization. I think I wedged it when I clicked it. Let's go back over to my recent. Oh, don't tell me I lost my experiment. I didn't. So the answer to the question again, we've actually done local interception, written them to local files, moved those local files up to Hadoop, ran a Hive query over them, and then from Azure ML and pulled that Hive, the result of that Hive query in, and that's where we started our model to build predictive modeling. So let's see if this is going to be a little bit. It should be much snappier there, but that's the way it should work. Let's add a Heisenberg. So what we're seeing here, folks, let's just do a quick experiment. This is an ROC curve. For those of you who are familiar with it, you know that basically it's the true positive versus the false positive rate for that holdout set. So a perfect model would have had all true positives, no false positives. A model that was flipping a coin would have ran the diagonal. You can see we've done a little bit better than that. And in fact, if you scroll down a little bit, you can actually see the confusion matrix. You can see a number of performance scores. But the short answer, this model isn't all that good. It's better than guessing. Let's see if we can do better. And again, we're going to try to push this experiment paradigm a little bit. I'm going to train another model really quick. And I know I'm going to need to train and score. So I'm going to clone those modules. I'm not going to train another perceptron, but I am going to train a boosted decision tree. I'll feed the boosted decision tree into the trainer. I'll feed the performance of the model to the same evaluate model to do a side-by-side. I'll click run again. Only the work that you have changed gets re-executed. Everything else stays the same. And again, we've done lineage and provenance tracking so that all the data from the previous run is retained as well. So while this guy is training, scoring, it's already done. And I gave it kind of a, let me just let it finish and then show you something. So right now it's doing the side-by-side evaluation, which is generating a lot of HTML5. It's done. I wanted to just click the boost decision tree. If you looked at it, we've just trained 100 trees in this ensemble. And for those of you who are understanding decision trees, each one of these is a machine learning algorithm. We've trained 100 of them together to actually help us make a decision. So that's an ensemble of machine learning algorithms in reality. We hope it does a little bit better. Let's see. Click visualize. And sure enough, significantly better. The ROC performance is much higher. Just click it. In fact, a good proxy for how accurate a model is, our previous perceptron, an area under the curve, which is just literally the area under this curve, is 68%. So it's a 68%, maybe 69% accurate algorithm. This one, on the other hand, 86%, almost 87%. We clearly have a winner here. What if we wanted to put this in production? We wanted to actually run our business on this. So let me show you how fast we can do this. Let's try to clear some room out here. Come on. Mouse is being finicky today, but that's okay. So I save this train model. So I'm going to save the machine learning algorithm, the train model that I just trained. It's saving it. New, experiment. Bring that train model back onto the palette. There it is. We overload the use of our scoring module to be a harness for building a web service. Now, a web service has to know what data. Oh, no, don't do that. What the incoming data looks like. So I say, look, for the web service, this is what incoming data is going to look like. For the web service, this is what the output should look like. Now, folks, we're really building an arbitrarily complex web service here. If I had modules that might write to a database, run a rules engine, I could have dragged them on and made that part of the scoring model I'm about to put into production as a web service. I'm just doing something very basic today, but literally, you can build an arbitrarily complex web service that uses machine learning and publish it. I click run. So what's going on behind the scenes is that it is looking at the data, building a REST API. It's done. I say publish. Would you like to publish this service? Yes. It's now talking to Azure. And we have just published a web service, not just one web service, but 2 web services to Azure, a request response web service, a batch web service. I could actually test the model running on Azure right now, just enter the metadata here and say, will this person buy a bike? Or if one of you said, yeah, I'll tell you my marital status, my gender, my income, my children, my education. Would I buy a bike or not? And we could test our predictive model right here in the actual environment in which it's going to run in production. Another cool thing is if you click this, and there is the URL, the OData endpoint for this model. Here's the URI for it. Scroll down a little bit further. If you wanted to write some code in Python, well, we've given you all of the REST headers associated with that for what the request body should look like, what a sample request should look like. Scroll down a little bit further, the response code your model's going to give you. Going a little faster because I wanted to show you this. We even generate the C# code to call this model. So you could copy, paste into your IDE, compile, and you're good to go. We generated it in Python as well. We generated it in R as well. So the time, not only we put the model in production, but we give you code to help you get it up and running. And if I go back here and I say, okay, let's do configuration. I like my service. Put it into production. Now the rest of the world can actually see this model and start making calls to it. That's the speed at which we can basically go from experimentation with different ML algorithms, writing a model, putting it into production as a web service, and people can immediately start calling it. So I'm going to stop the demo there and just kind of go back and just say a few closing words before we open for questions. I mean, we're doing this on the cloud because we see a world where devices, vehicles, and other devices will be sending data to the cloud for learning over, but also trying to make informed decisions. There's no reason why your vehicles can't tell you in advance when they're going to fail. We have customers right now monitoring fleets of vehicles. We have university groups who are doing predictive models for when a car is going to fail or when it needs energy for electric vehicle. So a lot of applications there. And it just to pull back a little bit. I mean, what's really making this happen? I mean, it really is the power of the cloud to support collaboration of crowdsourcing and collaboration, the ability to have large-scale machine learning and analytics, because you need it when you're learning, but when you're done, the machine learning model is so small, so fast, it could be integrated into small devices. So it really is the cloud where we think everything comes together: scalable machine learning, cheap storage of data, all the compute you need when you need it for machine learning. So just a couple closing comments. Again, I wanted to remind you about the Azure for Machine Learning award program that Microsoft Research is hosting or is operating for academics and nonprofit institutions. The first call for proposals will be for September 15th, the next round for November 15th, and they've also got, this is part of a broader Microsoft Azure for Research program as well, which you can actually get grants for using Azure for your research project as well, not just Azure ML. And a few things to point out: you can actually sign up for a free trial of Azure ML and play with it. If you don't want to wait for the academic awards, or if you're in industry, you can get access to it. We've actually put up a machine learning center, which basically has tutorials on how to use the service, samples, and a community we're trying to build around machine learning at it. We also have a blog that we try to keep in contact with our users and our customers as well. So with that, I would like to stop and see if we can just take questions in the time that we have remaining.
Okay, great.
Okay.
We do have a few more questions. Regarding IT question, is there any documentation available?
So there's documentation on the entire service, the modules, of all. If you're asking about that particular scenario of how we built it, that would require a white paper. We will be preparing a white paper on that. But the actual service itself, if you go to our ML Machine Learning Center, you'll find full documentation on the service, the modules, samples, videos to get you up and running.
Okay, thank you. And with the large variety of different tools and information moving between different platforms, how much information will there be available on performance impact of each component on the palette?
Yeah, that's a good question. So we actually get micro data. You can actually click a module in an experiment run. And something I didn't show you, by the way, is you can actually go back in time and go back to previous versions of your experiment. But you can click a module and you can say, hey, that module took this much time. That's a bottleneck in my machine learning. Let me try another algorithm that might run faster. So we give you performance data on each individual module as well as the entire experiment, how long it took to run. So hopefully that answers the question.
Okay, and will the presenter be covering how the pricing model will work for Azure ML?
Okay, so our current public preview pricing, I'll tell you what the spirit of it is. The actual numbers I'll have to pull out of some file somewhere. But the current public preview pricing is literally we're doing COGS recovery for ML Studio. That is, we only charge you when you're sitting there staring at the screen. You're not incurring a dime's worth of CPU or cost. When you hit run and your experiment actually starts to consume CPU cycles, then and only then are we actually charging, counting how much CPU got burned. And that's basically what we're charging, a chargeback for just COGS recovery for the CPU cycles that were burned while for experimentation, which really brings the cost down. Now, when a model gets put into production, we have a per prediction price. And if your model happens to be incredibly compute intensive, we actually charge for the compute as well. So that's the rough outline of what the pricing model is, at least for the public preview, until we understand how people use it, how much compute they use, and what, if we could have a package deal where we sell blocks of compute time. So we're still figuring that out in our public preview.
Okay, and it looks like we have one last question. Is there support for probabilistic programming in Azure ML?
Not at present. We do have technology here within Microsoft and Microsoft Research that will be pulling it in and offering that functionality as modules as well. As well as support for things like simulation and optimization as over time as well, modules that do that. But again, with that SDK that we're going to be making available later this year, if you find a good probabilistic learner or probabilistic or simulation package or rules engines that you want to incorporate, the ability to wrap that up as a module, put that into your workspace for your team to use is always going to be an option for you.
Okay, and one last question. What is the best internal contact?
So we have a support alias. Somebody can start with me for internal, just Barga, B-A-R-G-A at Microsoft.com, and I'll make sure it gets routed to the right person or address the question myself if I can.
Okay, and one more. When will Azure ML be available in the Dublin Data Center?
That's top priority on our list. We will GA with it in the Dublin Data Center and the Amsterdam Data Center, and there are other data centers I don't want to get into. But our GA roadmap, like all Azure services, is to make sure we roll it out to all of our data centers by GA. And so I won't talk about a GA roadmap, but I certainly don't want to. We don't want to sit on this service for too long. It'll be moving forward fast.
Okay, that looks like that's all our questions.
All right, well, thank you, everybody, for your time this morning. I know for some of you it was early, some of you it was late, so I appreciate everyone tuning in for the talk, and I look forward to any feedback you might have on our service and how we might help.
Great, thank you, Roger. We hope that you found today's information helpful. If you enjoyed today's webcast or have feedback on how we can provide you with a better event, please let us know by completing our survey. You should see the link to the survey in a pop-up window on your screen. And all materials from today's presentation will be available on the archive page within 48 hours. I'd like to extend a big thank you to our presenter, Roger. This concludes today's webcast. You may now disconnect from the call.